Hi, you guys, back, and I'm doing third video of the week, so let's hope that I actually get to posting all of these. Anyways, part B of this same problem 5.30. Okay, so let's just read the problem again. Some sliding rocks approach the base of a hill with a speed of 12 meters per second. The hill rises at 36 degrees above the horizontal and has coefficients of kinetic friction and static friction of 0.45 and 0.65 respectively with these rocks. Find the acceleration of the rocks as they slide up the hill, which we already did in the last video. And B, once a rock reaches its highest point, will it stay there or slide down the hill? If it stays, show why. If it slides, find the acceleration on the way down. So as you already saw in the last video, I claimed that this problem is so elegant, and you probably saw why, because everything just cancels out and you end up with this perfect, like acceleration is equal to, gravity times cos 36 mu k plus sine 36. All right, so now it's asking something else. Once the rock reaches its highest point, does it stay or does it fall down? So let's go ahead and draw another diagram. Okay, so let's say that, I don't like that. Okay, let's say that this is the diagram. So this is 36 degrees. That's the slope of the hill. Then we have some rock, right? And let's say that, this is the highest point, right? So we're just going to make an assumption. This diagram is at highest point. Okay. So nothing really changes in terms of like how we set up the problem last time, right? So we still have gravity that's pointing downwards, right? That didn't change. Normal force is still going to be perpendicular to the surface the object's in contact with, right? That's normal force. And then now, now we have something a little bit interesting. Now we don't know what direction. We know there's some type of static friction, even momentarily, but we don't know what direction it's in, right? So, for example, if well, actually, no, we do know which direction it's in. I take that back. We don't know what's going on exactly with static friction, right? So, what do I mean by that? Well, if the motion of this rock is downwards, right, then we know that static friction will oppose, right? Static friction will be this way, right? On the other hand, um, if it's just in place, then, we're not like static friction is sort of acting in both directions, right? Um, why? Because it's not moving up or down. Okay. So, but, okay. All right. So, how do we know if it will stay there or if it's going to slide downhill? Okay. So we know that if the force of static friction is greater than, any force that's going this way, then we know that, if static friction is greater, then that means um, the box doesn't move. That makes sense, right? Because if static friction is greater, then it's not moving. However, if static friction is less than any forces that are acting this way, oh, sorry, that was my oven. Okay. If static friction is less than any force that's, acting in this direction, then the box is going to slide down. That makes sense. Logically, think about it, right? Box does. Box does move down. Not box. Why am I saying box? That's so weird. Um, rock. So we're gonna write that again. Okay. Rock Rock doesn't move. And rock will slide down. Right? Okay, so let's let's go back. I said if there's any force acting in this direction. Do you see any force acting in this direction? It's definitely not normal force because normal force is perpendicular, right? It's not force of direct friction because that's literally the opposite direction. But FG is downwards, right? And downwards, like we said in the last video, there's going to be some component over here, right? So this component, right, which we said in the last video, you can check back there, but we said in the last video, oh, actually, one sec. No, that's such a horrible, okay. Okay, that's better. So we said this is 36 degrees, right? This is 90, and we don't really care what this is, but it's 90 minus 36, okay? But we know that this component over here, which is this one over here, that is going to be, no, this is FG. This one over here is going to be, I'm going to do that in a different color so it makes more sense. This over here is going to be FG sine 36, right? Like we said in the last video. So we know that, okay, yeah, FG sine 36. So that is the force that's acting in this direction. So what is it greater than? This, Fs, I'm going to write that down again just because it looks like greater than, greater than what? This what is Fg sine 36. Okay? All right. So yeah, the box is going to slide down if Fs is greater than this, and if Fs is less than this, then, the box will slide down. Okay. All right. So now we just have to solve for Fs, force of static friction, and Fg sine theta, which is Fg sine 36, and figure out which one is greater, right? So like the alligator is always going to want to open its mouth towards the bigger value. What is the bigger value? Okay, so let's start with this. Force of static friction. Well, we said before that force of static friction is normal force times mu s, and we already solved for normal force in the last video, which you can, look back at. We said normal force, we solved it to be Fg cos 36, right? That's Fn. And then mu s, that's Fs. That's our force of static friction, okay? And then we're comparing that to Fg sine 36. Okay, so Fg sine 36, actually, one second. So now we're comparing Fg cos 36 mu s, right? Compared to Fg sine 36. So is it this way? Are they equal to each other, or is it this sign, right? We don't know. But before we do that, we can just get rid of this Fg because they're both multiplied by a factor of Fg, right? So we can just get rid of that. Plus, it's not like we have our mass. We don't know the mass of the rock, so it's just easier to eliminate it altogether. Because if we divide both sides by 1, both sides by 10, we're not really compromising on like the value. Or sorry, not the value, but we're not compromising on which one is greater or which one is less, right? Because if we treat both sides equally, then it's fine. Okay. All right, so now cos 36 times mu s. Mu s is 0.65. So cos 36 times mu s times 0.65 is equal to 0.52. And then sine 36 is equal to 0.59, right? All right. So what's greater? Clearly, sine 36 is greater. So that means that this force is greater than the force of static friction. So we know that, I'm going to use a different color, Fg sine 36 is greater than Fs, right? So we know that once it reaches its highest point, it will slide down the hill, right? It will slide down the hill. Okay. Um, find its acceleration on the way down. Okay, so how do we find the acceleration? Well, like we said in one of our other videos, I think, was it in the last video? Actually, it wasn't the last video. It was in part A of this. The forces in the x direction, right? So this is our x direction, right? The forces in the x direction, um, we can, like all the forces that are acting in the x direction, is equal to the mass times acceleration, right? Because mass times acceleration is force. All we have to do is solve for A. So what we have to do is if we just write down or list all of our forces in the x direction and equate that to mass times acceleration, then we just have to solve for acceleration. So we have Fg sine 36, right? So this force that's in this direction minus Fg minus Fs, which is Fg cos 36 mu s minus, I'm just going to write Fs because we did solve for that. That is equal to ma, mass times acceleration, right? And we said that Fg, I'm just going to write that down, Fg sine 36 minus Fg cos 36 mu s is equal to ma, right? Then um, we can rewrite Fg is equal to mg, right? So mg, and I'm just going to pull that factor. I'm going to pull out both Fg. So mg sine 36 minus cos 36 mu s is equal to ma. Divide both sides by m. Acceleration is equal to g sine 36 minus mu s cos 36. And when we plug that into our calculator, what do we get? Plug that in one more time. Not getting the right answer. All right, one last time. Sine 36 minus 0.65 times cos 36. Oddly enough, I'm getting 0.61 meters per second squared. All right, that is our solution. Thank you so much for watching. If that was helpful, please don't forget to like, subscribe, share, do everything that will support this video. Thank you so much for watching and see you next time. Bye.